Let's go over this pulley example that we started in class and went over a little bit. The example is a asymmetric ramp with a pulley on top, so the two masses on either side of the ramp are connected by a rope that runs over the pulley. The first side with mass 1 has an angle of 45 degrees. The other side has an angle of 30 degrees. Mass 1 is known, it's 10 kilograms, and we want to find mass 2 such that the two masses balance on this frictionless ramp, and there is no motion. All right. So because we are looking for a situation where there's no motion, we're looking for an equilibrium situation, which means that we're looking to find the net force equal to 0, right? And that means that we can basically sum up the x components of the force, and that has to equal to 0. And we can sum up the y components of the force, and that has to equal to 0. But for motion on this inclined ramp, it doesn't really make sense to work in a coordinate system of x and y being horizontal and vertical. It makes a lot more sense to work in a coordinate system where we define, say, x prime to point along the ramp and y prime to point perpendicular to that ramp surface. And maybe on this side, we might choose a coordinate system, we'll call it x double prime. So we'll call this x double prime, and this y double prime that runs along and perpendicular to the incline on this side. Okay, so we are going to say that we have fx prime and fy prime being equal to 0, and of course when we deal with the second mass it will be fx double prime and fy double prime equal to 0. All right, so let's take one at a time. All right, so again we have a coordinate system here where we'll have x prime pointing along the ramp and y prime pointing perpendicular to the ramp, and then we will draw the gravity acting on the mass always acts straight down. But then what we're going to do is we're going to decompose that force of gravity, that acceleration due to gravity, along the x prime and y prime components, right? So this has a component like this and a component like this, right? These two vectors would add up by vector addition. Sorry about that. These two vectors would add up by vector addition to give this vector. Okay, so in other words, if we labeled this vector, this straight down vector, as just g, then this component along the y prime axis we'll label as g y prime, and then we take a second vector and add that to it, and that's our g x prime. That's this vector, and that together gives us g, right? But then the thing to notice is that this angle here is the same as this angle here, and we've gone over that in class, so I won't belabor that point. But this angle and this angle are similar angles because of similar triangles, so they're the same angle actually. And if we now look at the trigonometry involved with this angle, sine of this angle will be the opposite, which is this guy, over the hypotenuse, which would be this guy, because the right triangle is right here, right? So that tells us that gx prime over g, it's the opposite over the hypotenuse, is sine of theta 1, which means that gx prime is equal to g sine theta 1, right? So we now have the component of g that is along the direction of possible motion, right, which is along this, up and down along this ramp. Okay, so what force would be associated with that? Well, Newton's second law says force is equal to mass times acceleration. In this case, the acceleration is g sine theta, but let's be careful. If we define the positive x-axis to be over here, pointing this way, up the ramp in this case, and the positive y prime axis to point this way, then you can see that the force of gravity acting along the ramp is actually acting in the minus x prime direction, right? So we'll write this as force of gravity is equal to m is equal to minus mg sine theta 1, right? And that's our force due to gravity. Okay, so if we want a situation where we're in equilibrium, where this block does not slide up or down, then there must be a counterbalancing force along this axis, along the x prime axis. And that force is due to the tension in this rope, right? So we'll draw another vector on another force on our vector diagram, or our free body diagram, and that is the tension due to the string. We'll call it T1, right? So then T1 plus the force due to gravity, those are the two forces that are acting on it in this x prime direction, and we said that that has to equal to 0 for equilibrium. Right? So now putting in the appropriate signs, that tells us that T1, which is positive, is going in the positive x prime direction, plus minus mg sine theta, because it's going in the negative x prime direction, is equal to 0 if it's to sit still, right? But that just means that T1 is equal to mg sine theta. Very good. Okay, we have done that. We have done mass 1. Well, we can repeat this process for mass 2. Right down here. Okay, so now here we have a different angle, and a different slope. So we'll draw our new axes here. We'll call this x double prime, and we'll call this for mass 2, and this will be y double prime for mass 2. Right. Gravity again pulls straight down, but that's not the most useful coordinate system for us. So we're going to translate it into this x prime and y prime coordinate system, or x prime double prime and y double prime coordinate system. And this force of gravity has, again, a component that is along here. So this is just g. This will now be g y double prime. And then, sorry, that's a little sloppy, y double prime. And we add to it the component along the x double prime axis, and we'll label that g x double prime. Okay. So we are interested in getting this component here, right? And that, you notice, is pointing along the positive x direction. So we'll say that force due to gravity on mass 2 is equal to m2 times gx. So we should write in the x double prime direction along the x double prime axis, because that's the direction that we're expecting things to move if they're going to. We have mg x double prime, which is equal to m2g sine of theta 2, right? By the same logic we did before. This angle is the same as this angle, and so sine of this angle, theta 2, is equal to the opposite over the hypotenuse. So that's gx double prime over g. Right, so gx double prime is g sine theta 2. Right, and again, if we want this one to sit still, then it must be, then the pull here, that's pulling the block this way due to gravity, must be counteracted by something, another force, and that's the tension in this string. Right? So the sum of the forces in the x double prime direction axis is, we have fg x double prime, right, which is all of this, right? I mean, I can put the x double prime here, fg x double prime minus tension 2, right? We'll call this one tension 2. And we give it a minus sign because the tension pulling up on this rope, on this block, is clearly in the minus x double prime direction, right? So that tells us that for equilibrium this has to be 0, and then we say that tension 2 is just equal to fg x double prime, or tension 2 is equal to m2 g sine theta 2. Right, so we have T2 is equal to m2 g sine theta 2. Back here we have T1 is equal to mg sine theta 1, and of course this should have been a m1. So let's go ahead and correct that real quick. That's an m1. Right, and then we go back and look at the whole scenario, and we realize that T1 and T2 are on the same string. And we know that this pulley only redirects the angle of the tension. It doesn't actually change the magnitude of the tension. So that means that T1, the magnitude of T1 has to equal the magnitude of T2. So we can write that out now. So therefore, bringing all this together, we have magnitude of T1 is equal to magnitude of T2. And when we have, and we work this out for all the masses being in equilibrium. And so we have mg sine theta 1, sorry, m1g1 sine theta 1 has to equal to m2g sine theta 2. And now, remember, what we're interested in is solving for mass 2. So we can say mass 2 is equal to, the g's cancel. Okay. So we have m1 sine theta 1, there should be a 2 over here, over sine of theta 2. And finally, we can plug in the numbers, and I think I'll leave that up to you guys, but it would just be 10 kilograms times sine of theta 1, which was 45 degrees, over sine of 30 degrees. And that would give you the mass that will counteract the, that will give you the mass that will counteract m1 on the other side to keep the entire system in balance. All right.